Good morning, everyone. Again, I think it's a good time now to start the best paper plenary session. So we'll have 3 talks in this session. We'll have about half an hour for each talk. We'll reserve about 5 minutes towards the end for the questions. So we have a mic here. So if you have questions, you can approach the mic, or alternately, we'll have a student who can move around the mic for questions. So let's start with the first talk. I think it's a very nice transition from the keynote, which was on Ethernet. And as you see the title here, this talk is going to talk about Ethernet issues in an in-car environment. So that's a very nice transition. And the speaker is Steinbach, who's a PhD candidate at the Hamburg University of Applied Sciences in Germany. He's got his bachelor's and master's from the same university, and he's a founding member of the CORE working group, where CORE stands for the Communication Over Real-Time Ethernet Group, and they look at communication technologies for time-critical applications. So let's all welcome Ajay.
Thank you very much for the kind introduction. After this perfect keynote, you are already warmed up with the topic Ethernet. And I would like to introduce to you the challenges of in-car networking today. So the work that I present was done together with my advisors, Franz Korf and Thomas Schmidt from Hamburg University of Applied Science, Tech Lin and Daniel Herrscher from BMW Group Wirth Research and Technology and BMW. And Aachen from Technical University of Berlin. And as a short side note, SP authors first met at the 36th LCN in 2011 in Bonn, and they decided to join their efforts of in-car networking. We would like to thank the LCN for bringing us together for this work. Let me start with a short overview of my talk. First, I would like to introduce to you the problem that we address in the work and our motivation. Afterwards, I would like to give you a short summary about the technologies used in some of our previous work. And then I will show you our evaluation and some results before I give you some hints how to overcome the problems that we found in our assessment. And of course, I finish with a short conclusion and our outlook. So, over more than the past 2 decades, the in-car network grew, and with new driver assistance and applications, new technologies are currently required to cope with the high bandwidth sensors such as laser scanners, radar sensors, or high-resolution cameras that are currently being introduced in the car. Today, we have an in-car network that is extremely heterogeneous. It is composed of several domain-specific systems such as the campus or flex rate or the control data or the mass bus for multimedia applications. Using Ethernet in cars is a new approach to overcome the current problems, and it promises us a lot. It's a mature technology, as we already heard today, offers high transmission bandwidth, has low prices for the components, and already has a lot of expert developers and tool chains available today. And thus it's not really surprising that Ethernet already is considered for or is already used for a limited set of applications in cars. But if we just throw Ethernet in the bucket of available in-car communication technologies, we only increase the heterogeneity of the network and the complexity. So we think the full benefit of Ethernet will only pay when we use it in a homogeneous backbone design that is slowly replacing legacy technologies. We already showed that under well-defined conditions, Ethernet is feasible for the hard real-time requirements of in-car communication, but we foresee that for the success of Ethernet in cars, an additional traffic class with low priority and high bandwidth is required. So we expect in the future applications such as software updates, diagnosis, light updates of databases, for example maps, or even offloading of computational intensive tasks into the cloud. So the question is, what happens to our real-time guarantees when we have such cross-traffic applications to our network? And with this work, we want to contribute such an assessment of this problem and also provide ways to mitigate the shortcomings that we found in our assessment. But let me first give you a little background on the protocols that are compatible for deployment in cars. Many previous assessments already concluded that standard raw Ethernet is not really suitable for the harsh real-time requirements of in-car networking that are requirements with end-to-end latencies down to 100 microseconds for the control data and approximately 25 milliseconds for the transmission of a whole video frame in an advanced driver system. So currently there are two major approaches to investigate and they are under test for the use in cars. So the first is event-triggered real-time Ethernet extensions, such as the IEEE 802.1q.AV from the ABB standard or the rate-constrained traffic, known from the avionic full duplex switch Ethernet. That's the Ethernet standard that is flying with us in our planes. These operate with strict priorities in combination with a traffic shaper that prevents bursts. And then there is a second opportunity that are the time-triggered extensions, with examples such as TT Ethernet or Profinet that are commercial products, or the scheduled traffic class that is currently being defined by the IEEE under 802.1q.BD. The time-triggered extensions also use strict priorities, but in the center of the concept is a schedule. So all messages in the schedule, in the network are scheduled, and the schedules are synchronously executed in a coordinated time-driven multiple access approach. Some more details on the first approach, Ethernet ABB. Ethernet ABB is a protocol suite standardized by the IEEE. It provides, besides other standards, queuing and forwarding rules in 802.1q.AV. And basically it offers three different traffic classes, where the first two are a bit similar. The stream reservation class A is based on the 1Q priorities, and it's extended by a credit-based shaping algorithm. And it offers a maximum end-to-end latency guarantee of over 7 hops, that is 2 milliseconds. And this latency is assured by allowing only the reservation of 70% of the total bandwidth of the path between the sender and the receiver. Then we have the stream reservation class B. It's basically the same, but has an end-to-end latency guarantee of only 15 milliseconds for the 7 hops. And then we have another traffic class with a low priority, that's the best effort traffic class that does not provide any guarantees. And then for the bandwidth reservation, there is a stream reservation protocol that is an online signaling protocol to reserve the bandwidth from the sender to the receiver, but of course you can also have a static configuration. Then on the other side, we have the time-triggered Ethernet. That is an extension to standard Ethernet for mixed critical applications. It was standardized by the Society of Automotive Engineers in 2011 under AS 6802. And the major concept of the time-triggered Ethernet is to offer also 3 different traffic classes. So the time-triggered traffic that has the highest priority in the network and is transmitted time-triggered in a cyclic schedule. So the schedules are offline designed, and the time-triggered traffic class requires a time synchronization among all the sending participants. Then we have the rate-constrained traffic class that is sent event-triggered and limits the available bandwidth for the sender. And it uses the media access policy of the avionic full duplex switch Ethernet, also known as the RIN 664 standard, that was basically driven by Airbus. And then we have the best effort traffic class has the lowest priority, can be transmitted when the sender otherwise would be idle. And that is the traffic class that we use for the cross traffic in our assessment. Also, the IEEE time-sensitive networking task group, that is the successor of the Internet MEP working group, is currently working on a scheduled time-triggered extension for Ethernet. And later in the results, we can see why that is a good thing to work on. But to give you a little idea how scheduled traffic works in Ethernet, I want to show you an example of the media access strategy, how it works in time-triggered Ethernet. So you can see the upper ECU that sends time-triggered real-time traffic in a fixed cycle. That may be, for example, the electronic stability program of your car. Then the middle ECU that realizes a video application, which is event-triggered rate constraint messages, for example, a front-facing camera. And then we have the lower ECU that is responsible for diagnosis and uses best effort frames. Basically collects diagnosis information. So on this first hop, as you can see, all use separate links. There will be no congestion, so no problem here. But then we have a critical path here with the next hop, and here the simultaneously arriving frames must be somehow buffered. The scheduled traffic defines that first all time-triggered packets are transmitted according to their schedule, so they have reserved slots in the time-synchronized network. And afterwards, the gaps are filled with rate constraint messages. And then the remaining bandwidth can be used for the best effort frames. So now let's go over to our evaluation of the cross-traffic in automotive real-time networks. For our evaluation, we use a discrete event-based simulation. The simulation was implemented for the HomeNet++ network simulation framework. And the simulation models for both protocols were developed at the Hamburg University of Applied Science and BMW. And most of the things that I show are open source, so if it is interesting for your work, just see our previous publications and you can download everything from our website. In this work, we made a comparative evaluation of the network by using realistic traffic flows that we derived from the configuration of a BMW series car, using a tree-based topology that was developed at BMW. We analyzed flows with rigid timing requirements of control data and driver systems, but also multimedia applications. And in focus of our evaluation are latency and jitter, of course, because that's the most important fact in a real-time network. But of course, we are also assessing other network metrics, for example, queue sizes or link utilization. The traffic model consists of a total of 142 different low bandwidth flows of control traffic with really hard real-time requirements. Then we have flows with high bandwidth and medium timing requirements for the camera-based driver assistance. And then we use multiple multimedia streams with high bandwidth and low timing requirements. And as it's an assessment of cross-traffic, we also burst the cross-traffic with a variable MTU. And we are using burst of 1 megabyte. All flows were assigned to the available traffic classes in Ethernet ADP. This is the traffic class E for multimedia and A for the driver assistance and control data. And in time-triggered Ethernet, we use the rate constraint message class for multimedia and camera, and the time-triggered and rate constraint traffic classes with the highest priority for the control data. And of course, in both cases, we use the best effort background class for the cross traffic. The topology that we considered consists of 22 nodes in total with 7 switches and 21 links. So the structure is a tree with 1 switch in the root. And in this network, there are certain regions where domains dominate, such as the control data that's most dominant in this region. Then we have the camera data that is dominant in this region, and then we have multimedia data that is dominant in this region. And then for the cross traffic, the default entry is the ECU for external data, so that usually represents a wireless uplink to the car. So that's enough for the background and our scenario. Let's go over for some results. First, I would like to show you some results for the camera streams. It's the driver assistance applications with camera. And the graph shows the end-to-end latency in relation to the increasing frame size of cross-traffic that we use. So the y-axis will show the latency, while the x-axis shows the packet size of the cross-traffic frames. So as you can see on the left, we start with the frame size of 0 byte, so we have no cross-traffic. But then we add the bursts and start with really small frames and go up to the maximum MTU of 1,500 bytes. And next you will see in black the average, and in red for the real-time networks, the more interesting part, the worst case. So shown here are the results first for the AEB streams, and in average you can see that it's really unlikely that real-time streams suffer from the cross traffic. But in the more interesting worst case, you can see that there is an impact, especially with the larger frames, that must be considered. Now the same scenario with the rate constraint messages. On average, the rate constraint traffic performs a little bit better. But in the worst case, the delays due to the cross traffic are even larger with the rate constraint. We did not use the time trigger traffic class in this use case, as the scheduled traffic does not really suit well for the video traffic that we have in this example. Because most current video codecs use a variable bit rate, and it's really difficult to schedule a stream that always changes the size of the frames. In the numbers of this example, we can clearly see the effect of cross-traffic on the latency. So with cross-traffic, especially using large frames, ABB really outperforms the rate constraint traffic, as it simply better suits the transport of video streams. With the largest frame size, we almost doubled the end-to-end latency of ABB, and we have an increase of 100 microseconds for rate constraint changing. But all these numbers are well within the application requirements of video streams, so we are okay with the numbers here. Now the more interesting part, the cross-traffic together with control traffic. So control traffic is the traffic that makes your car work. And as automotive control traffic consists of a lot of messages that are transferred in cycles, we add the time trigger traffic class here. But first again, the results for Ethernet ABB. And you can see here that Ethernet ABB exceptionally suffers already using small frames. Then we have in comparison the rate constraint traffic class that is already shows a huge advantage and more linear increase here. But of course, we have the best results. The best results are obtained with the scheduled time triggered messages that we have here. So as far as the total determinism and no interference with the time triggered messages, we can see the control data is really uninfluenced by the cross traffic. That is really attractive. You can see here that the worst case is over the average, so there's a really small jitter when we add the cross traffic. This is even more obvious in the numbers. When we see the time triggered messages with really excellent end-to-end latency guarantees here, ABB and rate constraint messages really heavily suffer. So for ABB, we have a jitter increase of 14 times compared to the network without cross traffic. So this is really huge. And if we think back on the latency requirements of 100 microseconds that I previously introduced, we are far away from complying with the network that is configured like that. So what have we seen so far? The best results were obtained with the scheduled time-triggered traffic, and we can fulfill really rigid latency requirements down to 100 microseconds end-to-end latency with the time-triggered message class. All event-triggered traffic classes on the other side really suffer from cross-traffic, with a latency increase up to 5 times, a jitter increase up to 14 times, so this is really, really bad for the network. So the question is, why don't we use time-triggered traffic then everywhere in the car? Scheduled traffic has its challenges. And as already was pointed out in the keynote, a scheduled design, a synchronized design is not really what you want. First of all, it's far from being usable plug and play, to generating schedules is complex and limits the flexibility once the system is deployed. And scheduled traffic wastes a lot of bandwidth and it needs reserved slots, for example. So it's really desirable to use time-triggered messages only for those messages that have extreme real-time requirements, and for all other tasks, we want to use event-triggered messages. So the question is, can we improve our design to still guarantee real-time transmission with cross-traffic? And it turns out, yes, that's possible. And I want to use the rest of this presentation to show you 5 elements to improve the timing in-car real-time networks that have cross-traffic. So these are shaping the cross-traffic, improving the topology, limiting the MTU, increasing the bandwidth, and introducing frame preemption. And of course, not all of these elements are applicable in every situation, so we need an assessment of a particular use case, what we can use. Let's start. One problem with cross-traffic is it's only partly under our control. Where it is under our control, we can define rules how to design communication of cross-traffic applications in a static approach. And where it is not, we have to prevent the cross-traffic from uncontrolled entering the network. And this will be done in the gateway for external data that can contain some sort of a firewall that artificially shapes the incoming cross-traffic. The next, the topology. Our results show that the latency increase of real-time traffic is proportional to the number of hops with concurrent cross-traffic. So with that in mind, we can build topologies that support concurrent cross-traffic. So below you see a typical series car with most important control units highlighted. And you can see that there is a huge cluster around the dashboard. So this leaves a lot of possibilities when designing new topologies. And we can place the entry of cross-traffic near those ECUs that are processing the background messages. And we want to avoid daisy chains. So due to the history of field bus systems, the automotive industry still likes the concept of chains, and chains are really attractive, especially for optional control units in the network, as these won't use already reserved switch ports. But for the performance, we see it's undesirable to use daisy chains. Then frame size. We already showed the impact of the frame size in the results, but usually cross-traffic consists of bursts of really large frames to efficiently transfer chunks of data without overhead. And in real-time networks, already the slightest delay of a frame can be a challenge, thus we have to go down to see the delays in a smaller scale. So a short example, the best effort frame arrives on a switch on one line card right before on another line card. Another real-time frame arrives, and as the switch is not aware of the upcoming real-time frame, it forwards the frame according to the entry time. So this causes a delay that is, in worst case, the transmission time of one full-size frame. So at 100 megabits per second and an MTU of 1,500 bytes, this is more than 125 microseconds. So now think back on our latency requirements of 100 microseconds. That's not really working out. If we limit the MTU, that means we have only smaller frames in the network, we can reduce this delay. And this, of course, is a trade-off. And now the cross-traffic requires smaller frames and has a larger overhead. Then another possibility, of course, is to increase the bandwidth. You usually associate the bandwidth with capacity, but it simply means you can transfer the same amount of data in a shorter time. And in this example, you can see the effect. We have the delay induced by the cross-traffic, but then we increase the bandwidth of the outgoing line card, and we can have a delay that's only 1/10 of the original delay. So important is that we have an automotive certified physical layer for gigabit Ethernet, and that's on its way. And we suggest to think about using gigabit Ethernet not only on saturated uplinks, but also on those links that have really challenging timing requirements. And last but not least, frame preemption. Frame preemption is a new topic in the IEEE and development in the time-sensitive networking group, and it allows on-demand splitting of frames in chunks of 64 bytes. So that means the largest frame that we cannot split is 127 bytes or 12 microseconds. So in practice, you can imagine our previous example, preemption on demand. So the low priority frame arrives, the frame is preempted, and the high priority frames, the so-called express traffic, can pass, and afterwards the rest is transferred. So this produces a delay comparable to an gigabit delay. But it also comes with a slight overhead. So as a conclusion, we think that we will see best effort cross-traffic in future in-car networks, and our analysis reveals while time-triggered traffic remains unaffected of cross-traffic flows, the event-triggered real-time traffic class really suffers from a huge performance drop when we add concurrent background messages. So in our specific case, we see 5 times higher latency and 14 times higher jitter. And to overcome these limitations, we presented optimization strategies and protocol improvements that reduce the impact of the cross-traffic. In our future work, we want to assess the standardization of frame preemption and see how in-car networks can make profit of it. We further analyze heterogeneous designs with field buses and real-time Ethernet in parallel. So we were asked for such mixed critical networks with field buses and real-time Ethernet in parallel, but we were not able to fit that in this work. But we have a demo in this afternoon session where I'm really happy to show you such mixed in-car networks. And finally, we are currently working on a real-world prototype. You can see some pictures here. This car drives with a real-time Ethernet backbone. You see the trunk here. And yeah, we will have some exciting test drives coming up soon. And with this, I would like to finish my talk. Thank you for your attention. I'm looking forward to answer your questions now, and I would be really happy to see you in the afternoon in the demo session. Thank you.
Have some time for questions. There's a mic here.
Hi, thank you for the nice presentation. I have 2 questions. The first one is, doesn't it make more sense to have different networks for different kind of traffic inside the car? That is, one network for control and diagnosis, another one for driver assist, and another one for entertainment?
Basically, that's what we have today. But the idea behind this uniform network that consolidates different timing constraints is that it's much cheaper. You only have to have all these components once, and you can also make the wires lighter in the car.
Okay, but we're going towards more automated vehicles, then control functions will become more demanding in terms of latency and that kind of thing. So
yeah.
That's a parenthesis. The other question is, I didn't see a comparison with the CAN bus performance. Is it
the CAN bus performance? Yeah, the CAN bus is like 30 years old, so it wouldn't be a really fair comparison to compare CAN with 500 kilobits with 100 megabit Ethernet. So what you have currently with the CAN bus is far away from what we are seeing here.
Yes, but I mean some applications, the Ethernet doesn't provide like acknowledgements on receiving something, which CAN bus provides.
Yeah.
So if you want to do a fair comparison, you would want to compare Ethernet and some other protocols on top of it?
Yeah, sure. That's a little bit what we heard in the keynote today. So Ethernet is basically the thing, the layer down that's responsible for transferring the packets. So if you really require acknowledgements for your application, you must do that on the layers on top. And of course, I really agree. That's a bit of a paradigm change for the automotive industry and requires a bit of work of the developers and change the ideas that are currently there. Thank you.
So, coming back to the separation of networks argument. As far as I know, in current cars, the CAN bus is separated to networks also for reasons of safety. So if a device, for example, my power window switch fails, it doesn't hurt the constant network. Would you be able to provide this low level? feature?
Yeah, absolutely. First of all, we have a switched network here. So if a component fails on the physical layer, that's not so much a problem because the link to the next switch is somehow isolated. And we can have some sort of protection in the switches, of course. The other thing is about security and safety. That's a little bit tough. You would say there are not so many people that are into the campus. So it opens up the possibility for a lot of more students, for example, opening their car and trying to connect their laptops with the car. But as we already see today, it doesn't work with the campus. So we need to have a security layer on top. And with the high bandwidth that we have with Ethernet, that's even possible. So today we have the campus with a payload of 8 bytes. You cannot do some sort of encryption there. That will be possible with Ethernet, of course.
You talk about minimizing the number of hops for reducing latencies. Is there a magic number that you figured out from the experiments that will be the maximum number of hops that we should use in car Ethernet networks?
Yeah, that's a bit of a difficult question. We see that we can achieve good performing topology with hops below 7 hops. But as the car is really limited, that should be enough for all applications to be within 7 hops.
So we did a simulation study, and my question is, the network was not that big, right? Couldn't you do an analytical performance evaluation?
Yeah, we also did an analytical performance evaluation. The major problem is that we wanted to apply realistic traffic streams, and that was really, really hard to put that in an analytical model. And it was much easier to do a network simulation there. But I know you would add that usually you would do a worst case timing analysis on an analytical model. Sure, I agree.
One last question. Last chance. Okay.
Thank you.
And let's welcome the second speaker, Renan, Fischer, Silva. So, Renan is a PhD student at Politecnica University in Catalunya. He's got his bachelor's and master's from the Federal University in Paraná in Brazil, and he works on energy efficiency for data centers. And he was also part of the European research project Euroserver. So please welcome Renan.
Thank you for the introduction. I'm glad to be here making on this section. I'm under supervision of Paul Carpenter, and I'm going to present our work, exploring interconnect energy savings under east-to-west traffic pattern of MapReduce clusters. I'm going to follow an introduction about the subject and the motivation for our work, and the results are split in 2 parts. The first part with the stall timer, and the second part with package coalescing, and later on with the conclusions about our work. So currently, energy consumption is a major issue that researchers are working on. In 2006, US data centers consumed about 3 billion kilowatt hours, and more currently in 2011, worldwide data centers were responsible for about 2% of the total worldwide electricity consumption. Only in US, it was consumed about 100 billion kilowatts with the cost of $7.4 billion per year. Breaking down the numbers of energy consumption, we have that servers consume about 70%, but network switches are responsible for 30% of the energy consumption. On network switches, the port transceivers only consume about 11%, but researchers show that when you perform a shutdown operation on ports, you also save energy on buffers and helps to cool down equipment, leading to opportunity to save energy on up to 65%. Also, CPU and memory and servers are responsible for more than half of their energy consumption. And since there's a lot of work to bring energy efficiency to CPUs and memory, and they are becoming more energy efficient, it's expected the network to consume a bigger proportion. So current data shows that it's between 5 and 10%. So we consider servers network interface to consume about 10%. What's the traffic that goes on this type of equipment? So currently Cisco shows that 75% of the traffic in data centers actually remains inside the data center. It's not the traffic that is going out on the north-south type of traffic where you are sending the traffic either to another data center or to the user. So this traffic is from server to server inside of the data center, and it's basically originated by offline applications that performs large-scale data analysis, or also offline applications that are part of the pipeline that used by online servers. So, for example, producing the index of the web, or also producing satellite images to create map tiles. Also, Cisco has the predictions that the traffic is going to increase on a rate of 32% per year. And therefore, the energy consumption is also expected to grow. Researchers also show that the typical utilization of the network is low, even though it's the bottleneck is considered to be one of the bottleneck of the systems. You have a lot of idle periods and gap between packets, so you have opportunities to save energy through energy proportionality. Since the MapReduce application model fits on the description of the applications that generate that 75% of traffic, it's used to large-scale data analysis, and is also targeted to fit in commodity hardware that generally use Ethernet cards because the price is low compared, for example, with InfiniBands that are much more expensive. About the Ethernet, we have the standard that brings energy efficient on the interconnect level. That's energy efficient Ethernet. The problem with energy efficient Ethernet is that we can name, for example, troubleshooting sections and white paper from Cisco, HP, and Dell, and they relate problems when you use energy efficient Ethernet. So, unless you are aware of the side effects that you can bring on your applications, a common practice is to disable it in production use. The final motivation for us was we wanted to answer the question: what happens when you use energy efficient Ethernet on MapReduce clusters? What's the performance impact, if there is any, and is there any potential for energy savings? So MapReduce is used today on the famous big data names, and it's used to process huge data centers on large commodity clusters. The framework is responsible for tasks as prioritization, task scheduling, data locality. With data locality, one monitors and redistributes the data storage and also re-executes the tasks. On this example, we have the maps being receiving the input. It's a part of the tasks, and they sort the output and send the output to reducers on call it shuffle phase. That's believed to be the phase of MapReduce that stresses the network at the most. And on this phase, we have all-to-all communications between the servers that are doing the map tasks and the servers that are being the reducers. And finally, the reducers are going to write the output on a distributed file system. And we have Apache Hadoop as being the most famous framework implementation of MapReduce programming model. On energy efficient Ethernet, it brings, it was approved in September of 2010, and brings low power idle that dynamically turns on and off links regarding the activity. So on this example, on this timeline, we have the link was active. After there is nothing to transmit, it goes to sleep. It remains quiet for a certain period of time, and it refreshes periodically to detect link down operations and also to keep the transceivers aligned. And when there is a frame to transmit, it waits the link and it becomes active again to transmit the frame. The standard defines the low-level mechanisms when you have to enter and leave the low-power idle mode. It's really fast, in order of microseconds, to sleep and to wake the link. On this table, we have what was approved for the standard so far. It's 100 megabit Ethernet, 1 gigabit Ethernet, and for 10 gigabit Ethernet. The minimum time that the link has to wake and the minimum time the link has to sleep. And we also have the time necessary to transmit a 1500 byte frame and a 150 byte frame. And considering the time to transmit the frames and also the time to sleep and wake the links, we have the efficiency per frame, where 1 gigabit Ethernet has the worst efficiency among these three standards, and in comparison with 10 gigabit Ethernet, it's 3 times worse. One way to do the way that the standard improves competition between vendors is not defining when you turn off the links. And when one thing that was proposed was previously was the stall timer that keeps links on for a certain period of time before it becomes idle. On A, we have the frame transmission. When there is nothing else to transmit, it starts a countdown. That's the stall timer. When it becomes idle, and when the countdown reaches the end, it goes to sleep. Continuing on B, after the refreshes and after it remains quiet in the refresh interval, if there is something to transmit, the links wake up and transmit the frame. We also have what happens on C, that sometimes you have small gaps that doesn't fit for the stall time, so you transmit the frame, start the countdown operation on the stall timer, and it doesn't reach 0, so it means that the frame will remain on, your interface will remain on, and you transmit the frame, and you have to count down the stall timer again. We go to the first set of our results. So first I'm going to explain our simulation environment. We decided to go with a really accurate simulator that statistics show that's one of the most used simulator nowadays, NS2, and it has an energy efficient Ethernet model, and we driven the traffic of the network with the Hadoop simulator that was developed by Virginia Tech. It's an MapReduce that generates synthetic MapReduce applications as TerraSort, Index, and Search, where they have different sizes when comparing the input and the output of each map. Originally, MapReduce was targeting batch processing, where you have huge data sets to be processed and you will power the whole cluster utilization. But recent tracers of Facebook show that it is evolving for what they call online streaming analysis, where you have just a few maps and one reducers, and we call it small tasks in our work. So we are going to simulate both batch processing and also the new trend that's small tasks. We simulate 3 different sizes of clusters with 24, 50, and 8 nodes divided in 2 racks with different network over subscription. So Cisco and also Hortonworks, that's a big player on MapReduce and big data, they recommend that you use network over subscriptions lower than 4:1, and then to show the different performance that you can achieve, we decided to go with these 3 sizes of clusters. So the servers are connected to top of rack switches
by 1 gigabit Ethernet, and the top of rack switch is connected to aggregation switch by 10 gigabit Ethernet. We simulated also with different buffers size on the switches as shallow buffer size of 128 kilobytes, and for more expensive switches using 10 megabytes per port, what's called the deep buffers. And we also used different TCP buffers, the TCP settings that are 64 kilobytes per connection, that's the default. And when you have optimized TCP buffers and you have the window scale option enabled to reach 1 megabyte per connection. First, we want to understand what you should expect. So we decided to carry on the experiment of delay impacts on link and what's the performance on MapReduce. So on the x-axis we have link delay in seconds, and the y-axis we have the runtime in seconds. And we see that for both batch processing and small tests, it's not expected to be MapReduce to be delay sensitive, not on the considering the time to wake and sleep the links of energy efficient Ethernet. Because for small tests, we see that after 100 microseconds on each link, you start to have performance decrease. Your performance starts to decrease. But for batch processing, it holds stable until you start to have delays on link of 5 milliseconds. In summary, we don't expect any performance degradation when using energy efficient Ethernet with the stall timer. So we continue the experiments using a simple stall timer that can vary from on the x-axis from 1 second to decrease until 1 nanosecond. And when it's about 1 second, it remains stable because the heartbeat of MapReduce was also of the MRPerf, our simulator was also 1 second. It means that the link almost never sleeps, and when it starts to decrease, the stall timer starts to become smaller, your link starts to sleep more periodically, and it may affect the performance, but this is our worst case scenario where we see a performance degradation of about only 1%. We also have a lot of noise when we decrease the stall timer, basically caused by TCP congestion control algorithm. On energy, what's the energy, following the impact on energy, we see that we have on the pink we have 1 gigabit Ethernet, green 10 gigabit Ethernet, and the average on data center. We see that while for 1 gigabit Ethernet, stall timer of 1 millisecond achieves the best energy savings and it remains stable, for 10 gigabit Ethernet, it's better to use a stall timer that's lower than 10 microseconds, therefore achieving the best energy savings. When we break down the numbers with our all scenarios, we have on the right batch processing with the different network over subscriptions. On the left, we have small tests. And comparing the legacy Ethernet with the standard IEEE, we have a huge improvement. And it doesn't matter if it's small tests or batch processing. But when we take a look on the ideal model, that's what it would be when you don't have to pay the penalty to sleep and wake up the links every time. There is still a lot of improvement that can be done for 10 gigabit Ethernet links. And how can we do that? There is a technique named package coalescing. Now, if you're not native English speaker, as I am not, maybe you never heard what's coalescing. So for me, the definition would be when you do package aggregation on the link buffer. You distribute the overhead among the packets, and you can do that on 2 ways. You can use a timer, or you can use a trigger. So on our example, on A, we don't have package coalescing. So after the stall timers, the link sleeps, it remains quiet, saving energy, but then it has to wake up to transmit one single frame. It transmits the frame, it has the countdown again of the stall timers, it goes to sleep because there's not to be transmitted, but then soon enough there is a frame arrival, and then you have to transmit the frame, you wake up the link again, and you transmit the frame, and so on. And this is like an example why you can have better energy savings on the 10 gigabit links. And then on B, you use package coalescing technique, where after the stall time, the frames arrive, but it remains on the low power idle mode, saving energy until either your timer or your buffer is triggered, and then you wake up the link again to transmit more frames, and then calm down again on the stall timer. This is a redraw picture of related work, and it shows that the baseline is no energy efficient Ethernet. It means like the legacy Ethernet. And comparing with energy efficient Ethernet, it shows that when the link utilization is only on 10%, the power used is about more than 50%. And then you start to use package coalescing, and it helps to get closer to the ideal model. So longer you coalesce packages, better are going to be your energy savings. The problem is that on this example, it didn't consider the performance of applications, it just considered latency. And it also used post-on arrivals. And now in our scenarios on MapReduce, we're more worried with the performance of applications, even though you can have more latency, a bigger latency using package coalescing. The last thing we need to cover just before going to the last part of the results is how TCP influentiates these results. So TCP was currently is IP traffic is currently the most used traffic in data centers. It can be either TCP or UDP, depending on your application. But Microsoft Research Centers they showed a study where on their data center, for example, TCP was responsible for 99% of the traffic, and TCP was originally targeting wide area networks. And when you put TCP on us, you have new type of problems. For example, you can have the incast problem, where you have many senders to one receiver, and causing leaking congestion on the last pipe before the receiver, and therefore you start to drop packets. You dramatically reduce the throughput, and you also have the outcast phenomenon, where surprisingly nodes that are more distant to the destination tended to have better throughput than nodes that are closer to the destination. So for example, the 12 flows that come from the aggregation switch, they tend to have a bigger throughput than S2 and S3 that are on the top of rack switch 1, that tend to have bigger throughput than S1 that's really close to the destination. This happened because the phenomenon described as port blackout. And one way to fix both incast and outcast problems is increasing the buffer of your switches. But this not only leads to a more expensive solution, it also leads to a new phenomenon that's also described as buffer bloat, where you start to increase the latency of your applications. In summary, the TCP settings and the switch buffer size are also critical to performance. Using package coalescing settings, we decided to go with the standard IEEE. That means no package coalescing. We call it NOPA on the slides to be shorter. And we also use the values that were used in related work. One publication used 12 microseconds, 10 packets, or 120 microseconds and 100 packets. And another publication used much bigger values as 1 millisecond or 10 milliseconds, both buffering 1,000 packets. So using package coalescing, first we consider the runtime, where on right we have deep buffer switches, on left we have shallow buffer switches, both with default TCP and tuned TCP settings. And the best runtimes we saw were the ones without package aggregation, 12 microseconds and 120 microseconds on the shallow buffer switches. On deep buffer switches, we can see that although 1 millisecond and 10 packets is considered to cause 20% performance degradation on shallow buffer switches, When you use deep buffer switches with tuned TCP, the problem is basically fixed, having only 1% of performance degradation. And 10 milliseconds and 1000 packets is practically forbidden for data center using MapReduce applications. On energy, we see following the same distribution right and left with deeper buffer and shallow buffer switches. We see that the best energy savings on shallow buffer switches was 120 microseconds. And when you go to deep buffer switches, you can, if you still use the default TCP settings, you can you have 120 microseconds and 1 millisecond really with similar energy savings. But when you use the deep buffer switches with tuned TCP, 1 millisecond starts to become becomes the best energy savings, mainly because the runtime of the application was also reduced and then reducing the energy consumption. In summary, what we could learn from that is that okay, you have deep buffer switches, you tune your TCP. The best savings are going to come with 1 millisecond and 1000 packets, and then you only have 1% of performance degradation. But that's the most expensive solution in terms of money, so you don't always want to go that, especially because MapReduce was meant for commodity hardware. So we decided to carry a new experiment that was targeting commodity switches with the 10 gigabit links that is still the ones that have opportunity to save energy, using 1 millisecond and 1000 packets. And on 1 gigabit Ethernet, we keep the original settings that was the two best settings on shallow buffer switches. That's 12 microseconds and 10 packets, or 120 microseconds and 100 packets. And when you see, we compare the uniform settings with our optimized settings regarding the 1 or 10 gigabit links, we see that the two best results came from when you use 1 millisecond and 1000 packets on 1 gigabit Ethernet. And it's easier to see when you break down numbers. When you see the 1 gigabit Ethernet energy profile, you see that actually there's not much room for improvement, because the ideal already shows that you could go with at the most 20% of improvements when you compare to standard energy efficient Ethernet. And when you see on 120 microseconds and 100 packets, it actually causes some burstness that lead to some loss of frames and therefore some retransmission, even though the runtime was not affected considerably. So with the retransmission, you also can have even worse energy consumption than the standard energy efficient Ethernet. But when you see the 10 gigabit energy consumption profile, it's easier to understand that there is too much room for improvement. When you see the ideal was that you can go up to 80% of energy improvement compared to the standard energy efficient Ethernet. And therefore, using optimized settings, you almost reach the ideal energy consumption. Our conclusions are on related work. We have energy efficiency on HPC that both on either use InfiniBand links, that's not Ethernet layer, it uses MPI layer, or also energy efficient Ethernet on HPC clusters. And also another activity research area in data center was with video streaming using UDP traffic, where they concluded that using TCP rather than UDP would lead to lower energy savings. As conclusions, we have for system administrators that energy efficient Ethernet, if you have switches and NICs that already offer the option, it can be turned on your MapReduce clusters, and you start to save energy with negligible performance degradation. For manufacturers, a simple install timer already offers good savings for energy savings for 1 gigabit links, but optimal energy savings only for 10 gigabit links are only possible with package coalescing that can help the energy improvements between 20 and 60% when you compare against standard energy efficient Ethernet. As future work, we plan to extend the study using a protocol that reacts fast to congestion and therefore reduce the buffer utilization of equipment that may lead to better results. That's all.
I have two questions. The first question is, so regarding the energy models of the hardware you consider, there are different vendors that have already energy efficient switches out there. So how do your results fit to these switches?
Okay, so on energy model, I didn't put all the numbers to not go too much the presentation. We have like the link power there, and on the paper there it's better described. There's a big range on the energy consumption of 1 gigabit Ethernet or 10 gigabit Ethernet. Basically, we did an average between vendors when they display the information, because sometimes the information is not explained, and we consider we see that on average 1 gigabit Ethernet consumes 5 less power than 10 gigabit Ethernet. That's what we consider.
Okay, and the second question is more the technical one. Seeing your plots, how is it about significance? You always show bars, but can you tell us a bit about how significant are the results? Some of the bars are pretty close together. Have you calculated confidence intervals, variations, whatever? So,
okay. So the simulator is deterministic. We had a big plot about the results that actually would be hard to go through on the description of each one, and we saw that in average the variability was small and basically caused by the TCP congestion control algorithms and the scheduling decisions. When you take the average on all the scenarios, that was the plot that we showed with the average on our scenarios. So considering the average, that was a
Yeah, hi. I have a question that I think that the energy saving would directly be related to the data localization concept of MapReduce. So, I mean, if your MapReduce cluster is able to utilize data localization, then, there won't be like much utilization of links, and that would affect the overall network power as well. So I don't know if you were able to control this using your NS2 simulation. That's one question.
No.
Okay, so that was not part of it, right? So, but I believe that would have a major impact on it. And the second question is that you mentioned about this packet collisions. I think this TCP also does that. So if you are controlling it at a lower level, probably I believe that TCP would have to follow that. Would that be a thing, or
TCP it does that on the upper layer.
Yes,
and you have to do it. But
yes, and that's automatic.
Yeah, but this is on the servers, and we consider the servers on the edge of the links on the network. But when you think about the switches, actually you don't have the TCP application there, right? So the switches are only forward packets, and then you have the ingress and egress buffers.
Right.
So that's why you have ingress, you have the buffer switch to accommodate the persons, the traffic. And then you want to transmit, when you have things to transmit on the egress port that goes to the destination.
Okay. So you also mentioned about this TCP incasting. So were you able to utilize this data center TCP from Microsoft, like TCP?
No.
You did.
It is available for
Yes.
for NS2 also, but when we implement, we put together the CTCP with our energy efficient Ethernet model. Actually, there was some problems that we weren't able to fix the problem until the publication of the paper. That's why we put as a future goal.
Thank you.
You've done all this for MapReduce. Now, how visualize not all traffic?
Yes. With this study, we expect that when you have applications that are not MapReduce but follow the model that you have dynamic scheduling, large data transfer, and they are not supposed to be data sensitive, regarding the topology that data centers, that's more or less some applications follow the same topology where you put this on the servers layer with 1 gigabit Ethernet, and on the access layer, top rack switches and application layer also with 10 gigabit Ethernet and similar network over subscriptions ratio, then we expect to have similar results, especially for the 10 gigabit Ethernets that are still power hungry, and there is still a lot of room for improvement compared to this under
Let's thank. Okay, now let's welcome the last speaker, Hanno Wirth from RWTH Aachen. Hanno is a postdoctoral researcher, and he's received his PhD from the same university. His research interests lie in wireless multi-op communication. And he's going to talk about collaborative on-demand Wi-Fi sharing. So please join me by thanks for the introduction.
Hi, I'm Hanno. I'm here to talk about on-demand Wi-Fi sharing and also the risks of not finding a good acronym for your project to the paper deadline. So that's why we're stuck with Klaus there. This is work with Thorsten, Martin, and Klaus. And there's a very simple motivation to start off. Internet access over Wi-Fi is a good thing, right? So we all use it, we all love it. But that's not necessarily why we're here. It's a commodity at home or at work or maybe at Starbucks. So you have wherever you go and wherever you need. But of course not wherever you go. So if you leave that comfort zone of your known environments where you have access to Wi-Fi networks, if you roam out of it, you don't have access to Wi-Fi networks that are not your own and that you don't have a trust relation to. In the words of Metcalf, they keep asking for Wi-Fi passwords. That's an annoying thing, I agree. So of course you could use LTE all the time, but of course your LTE data plan could be slow, could be throttled, could be capped. You could have a huge file transfer. You could be underground abroad in rural areas. So there's a lot of places where the LTE network does not necessarily reach you with the quality you want. But then there's the question that the Wi-Fi networks and broadband internet uplinks behind them are ubiquitous, so why don't we just share them? And to validate the statement about the ubiquity of Wi-Fi networks, we could look at Wiggle. This is New York, this is Sydney, and they're practically bursting with potential for the Wi-Fi sharing of private Wi-Fi networks. And even in smaller cities like Aachen, you see that you do have networks nearly in every street. So you have a wide spread potential to share Wi-Fi networks. So why don't we share it? Well, it's an either-or decision. Either you give them access to your network or you don't. If you don't give them access, that's the state we're having right now. So, okay? If you do, you face security and liability risks. For instance, you're not aware and not necessarily sure what users could do in terms of malicious systems once they access your network, so you have no control over that. And second, typically you're liable for all the internet traffic that comes out of your router towards the internet, so if there's any bad, malicious, illegal traffic, you're serving as the point of contact for that. And of course, the solution for that is authentication. Authentication of the roaming client of the mobile user. And that serves also as the related work or comparison of the state of the art. This comes in 3 flavors. First, you have a centralized approach where if you happen to find an access point of the network of, for example, the phone or another commercial provider, you associate to that access point and the access point authenticates you towards the centralized provider instance. Second version is in organizations, in the EduRoam organization or in the Hotspot 2.0 movement, you have hierarchical H2.1x authentication, so the access point of the foreign organization forwards the authentication request to the foreign router, foreign radio server, and that authenticates you against your home radio server, and if that's possible, positive, you get access to the network. And third,
There are grassroots Wi-Fi sharing communities where the communities are made up of private access point owners, and if you happen to come across one of these access points, you are authenticated by this access point within the community. At the community operator or provider, and that could be a centralized or a distributed instance, so that's a step forward. Of course, all these three approaches have their drawbacks, namely in the provider instance, it's only a single provider, so you need to find a network that belongs to this provider, and that means you have a limited number of networks available. In the organizational approach, you need to adapt to the infrastructure requirements. That is, you need to operate a radio server, and you need to be integrated in the hierarchy of authentication, in the chain of authentication somehow, and that's not possible for private access point owners. And in the third approach, while Wi-Fi sharing communities are a nice thing, they have limited uptake, that means limited user bases, and with that, a limited number of networks, and again, you're bound to the one access point that is serving the community you're part of. And from a more technical point of view, and that's the point we're attacking in this paper, is you always need to, whether you, in any of these three approaches, you always need to serve one network for the approach you're participating in, and that permanently, doesn't matter if someone's there who wants to use it or not, you operate that network. And, more importantly, you give the roaming client access to the network without authenticating him beforehand, or even without authentication at all. And that's, of course, so in this paper we propose a solution to that, namely cooperative on-demand Wi-Fi sharing, or COWS. And we want to achieve the following goals. We would like to leverage the ubiquity of private Wi-Fi networks for Wi-Fi sharing. It doesn't matter which community or provider concept you're a part of, and we would like to be able to support arbitrary incentive schemes based on that cooperative sharing approach. And last, very important for me, we would like to be compatible to real-life devices, real-life settings. And the main two technical contributions of our approach of COWS is that we only instantiate those sharing network on demand, that is when a client is there who wants to use this, who expresses interest to use that sharing network. And we only grant access to the network to the client after we authenticate it. So we want to be on the safe side there. In a schematic overview, it looks like this. We have a roaming client who wants to use the internet, and we have access points surrounding the client. And whereas in the previous approaches you would need to find and pick the one access point that serves your community or provider or organizational approach, in this approach, the client simply asks all the Wi-Fi devices in the environment, in the surroundings, for a Wi-Fi sharing network. That is, he broadcasts a request for a Wi-Fi sharing network stating literally, I would like to have that. And all devices that overhear this request become eligible, or are eligible in our approach, to serve as the sharing access point. So that means the access point itself can decide whether it serves the request or whether it doesn't. And eventually, if one access point decides to serve that request, it forwards the request for a sharing network to the home network provider, be it cellular or internet, broadband internet, of the roaming client, and authenticates the client at this provider. And if that authentication is positive, he instantiates a network for the client associates to that network, and then can use the internet. In a more detailed overview, the client sends the request, the access point authenticates the client at the home provider. The provider gives back to the access point the information needed to instantiate the network for that specific client at that specific point in time, and the access point instantiates that network for the client to join. And one part that wasn't in the previous slide is the dashed line coming from the client and going to the home provider. Since the client doesn't trust the access point and the access point doesn't trust the client, we tunnel all client traffic over the access point to the home provider, meaning that all internet traffic then originates from the home provider and not from the access point. And it's hidden from the access. Okay. So a few assumptions. There's no trust between any of the parties. Of course, the home provider knows the client and the client knows the home provider, but the access point doesn't trust the home provider, and it doesn't trust the client, but he can hold the third party accountable for actions that the client takes, and that is the home provider. That's a public entity. You can always do accounting with them and always hold them accountable. Prerequisites to start our approach are the following. The user should register for this specific type of roaming service at the provider, and that's just to establish authentication credentials, which is needed in any case. So we have a public-private key pair, that's normal. And more importantly for our approach, we need authentication credentials in the form of a user ID for the client and authentication tokens. And authentication tokens in our approach are tokens of a hash chain, which we disclose in reverse order, and with an element that you receive, HN, you can check whether that's valid by comparing it, simply by hashing it, to a previously received element HN plus 1. Furthermore, we publicly identify providers, the provider ID, and that's just the combination of the mobile country code and the mobile network code. That gives you a 6-digit identifier for providers, and all the providers that you can think of are typically represented by such an identifier. For example, the Verizon USA provider would be the number you see there, and that works for providers. Back to the design. So the client, as said, requests the Wi-Fi sharing network by simply broadcasting that request, but there's no communication link available between the client and any of the Wi-Fi devices around him. So what we do is we embed this request in an 802.11 probe request. That is literally a request for a network as used in 802.11, and that is a broadcast that's observable by our Wi-Fi devices, so every Wi-Fi device can read that, process that, and maybe do something with it. Of course, that's a bit deviating from the norm, because normally we request networks by name, by their SSID, and now we do something else. Namely, we broadcast the network request and give the authentication credentials for the client in that request. That is the user ID and the current, the fresh authentication token HI. And because we don't trust the access point and we don't trust anyone around us, we encrypt that using AES counter mode, using the index I of the current authentication token to construct an initialization vector. And so we can send that, and the probe request looks like this. You have the prefix that identifies this request as belonging to our approach. You have a provider ID, that's public, we don't need to hide that. You have in blue encrypted the authentication token and the user ID, which is the private information we want to transmit, but don't want to see anyone to see it. And we need 5 bytes of ASCII-85 conversion to put the non-ASCII 85 characters from the authentication token user ID into the probe request. So we send that, and then we send it to the access point, but the access point still doesn't know what to do with it, and because we don't have any trust relational authentication credentials established with the access point, can't do anything with it, so it forwards this authentication request to the home provider. You can easily look up the provider by using PID, the provider ID, and he attaches the MAC address of the client. So in essence, the aforementioned probe request gets forwarded like this. It attaches the MAC address of the client to the provider, forwards that to the provider for authentication, because he doesn't know the client and would like someone accountable to serve as an authentication proxy for that request. So is that client a good guy? Should I give him a network or not? At the home provider, the authentication works as follows. The provider looks up the current, the last received authentication token, HI plus 1, for that MAC address, for that client. And he calculates the AES initialization vector using the next index I. That's just a number you can just. And with that initialization vector and AES, he decrypts the request and gets back the user ID and the hash, the authentication token. And then you can verify whether that's a benign and a fresh request by just hashing the received element and to see whether the hash value then relates to the previously received authentication token HI. So let's say this authentication works as I described and it's positive. then we still do not have a Wi-Fi network or any sort of communication channel between the client and the access point, but we would like to instantiate a network specifically for that roaming request for that client. So the provider calculates the details you need to instantiate the Wi-Fi network, namely the network SSID and the WPA key for that network. But since we do not have a communication channel from the home provider to the access point to the client needs to do the same autonomously without asking anyone or without having a communication channel. So we do it like it's on the slide. We need the current authentication token that we did not reveal to anyone. We hash it, and we take the first half of the resulting substring to create the SSID of the resulting network, the second half of the resulting substring to create the key for that network. Those we can send back to the access point in a secure manner, without always without revealing the authentication token, so as not to corrupt the hash chain. When the access point receives this information, you can easily, on the fly, instantiate a Wi-Fi network. Yes, you can easily instantiate a Wi-Fi network for that specific details. And 2 points here. Using wireless network virtualization, we can instantiate more than one network. That is, we do not need to turn off the Wi-Fi network of the access point owner, and we can serve multiple clients at a time. And we can also, because we instantiate the network on demand, at network instantiation time, establish traffic shaping rules or techniques per network, so we don't need to rely on the client being nice and not using a lot of that. Okay, so once the access point instantiates the network, the client can search for it and has all the details necessary to connect to that network, namely the SSID and the WPA key. And once he's established the connection to the network, he can, in essence, communicate. But remember that the client doesn't trust the access point, and the access point doesn't trust the client. So the access point evades this liability issue that I mentioned in the beginning by tunneling everything the client sends to the home provider. So we establish a secure tunnel between the access point and the home provider, so that the access point is liable for the traffic. Because the client doesn't trust the access point either and doesn't want him to look at the traffic or manipulate the traffic, the client tunnels everything he sends to the home provider as well. So we need something in terms of a VPN tunnel or encrypted packet tunnel. So we hide the traffic from the access point, and the access point is not liable for the traffic the client sends. Of course, since we talk about security, we should look at what the security considerations of our approach are. First, we could have a passive attacker that simply snoops all the packets we send or the data we send, and he could capture and maybe replay a request quicker than the client sends that. And if he is able to do that, the request is fresh and is valid. So the provider would authenticate that request and would send back the details to the access point. The access point would instantiate the network, but then the passive attacker would still have no means of accessing the network, since he does lack the credentials to calculate the SSID or the WPA2 key. So there's no problem with the passive attacker, although it's annoyance. If the access point is malicious, he could take the instantiated access network coming from the home provider and open it up to everyone. So that is easily possible, but there's no gain in that. Because you can't, and no client can construct a tunnel to the home provider except a valid, a benign client. And if the access point just opens up that network to everyone, the internet traffic originating from that open network originates from its own access point. So there's actually harm for the access point in doing it. If he simply wants to drop all the requests he sees, or simply wants to drop answers from the home provider, that's equivalent to not participating in our scheme. And since we talk about a collaborative scheme, and we can't force people to collaborate or to cooperate, that's bad, but it doesn't hurt the system as such. So it's still operable, the client just won't get in. And last, we could have an active attacker. An active attacker could overhear requests, capture the MAC address that the access point attaches to the forwarded request, and could try to flood or spoof requests going to the provider. The provider couldn't distinguish between the attacker and the correct working access point. So while the attacker cannot correctly encrypt or decrypt the request because he doesn't have the credentials, he could just simply flood and try brute force to guess the correct request. That would lead to the provider trying to decipher all the requests that arrive at the provider, and that is work, of course. And we come back to that later in the evaluation, but we'll see that it's not hard. So we implemented this. I think I'm the only one here who didn't simulate in this approach, but we had all these devices lying around. So we implemented this for Android mobile devices, and we realized the access point with a Linux IdeaPad using open source host APD software, so that's the normal way of doing that. And for the home provider, we realized two settings. One instance in a local network at the university, and that serves as a baseline since the communication cost and overhead is minimal. So we can see what our approach actually transports in terms of occurs in terms of overhead. And then we used Amazon instances to relocate the provider instance. Since we're talking about Wi-Fi sharing, if your home provider typically isn't in the same network as you are at the moment. So it could be either in the same city or in the same country or even somewhere else. So we looked at two evaluation criteria in particular. First, time overhead, and second is the cost of security. So, as I said, for the active attacker. Let's first look at the time overhead of the full procedure that we looked at for a single network instantiation. I only show the values as observed on the client. In the paper, we made a clear distinction where the time goes, the time overhead occurs in terms of every participating entity, so you're welcome to look that up. We'll only look at the timing as observed in the client. And for step 5, as mentioned in the overall overview, we do an open VPN connection in certificate mode, which is the most heavy mode OpenVPN supports, and it's a rather bulky implementation, so we could definitely decrease the time used for that. It's just for proof of concept. So we see that no matter if the provider is located on a local network or in the same country, for us it's Frankfurt, or on the US West Coast, that means transatlantic data forwarding step is included in the procedure. The confirmation of the request we had, step 1 to the left, happens within 1.5 seconds. So that's okay. That's when the access point has instantiated the network and the client has observed that. And step 4, Wi-Fi setup, and step 4, Wi-Fi connection established, that's Android. The typical Android time overhead we need when we want to connect to a network. And that's about 2.8 seconds, so in total we're talking about 3.8 to 4.5 seconds, depending on where the provider is. And we see that no matter where the provider is, it doesn't have much influence on the time overhead, except for the VPN establishment. There we have a lot of round trips, and there the increased round trip times make a difference. If we have multiple users, as it is to be expected in a crowded environment, we would like to serve every one of these users until we're out of capacity. So we realized that using RWTH 9K and host APD, we can virtualize multiple networks on one access point. For our setting, it was 4. And you see that in step 1 and in step 4, you see that there's contention for the wireless link as well as for the access point functionality. So there's a minimum of an up and down, depending on which client sends which request first and which client does the scan first, etc. And there's also a minimal increase in the processing time on the access point because it receives multiple requests simultaneously. However, again, not shown here, there's no increase in the provider processing time since we only use AES and hash operations in those on microbit. So that's possible too. So we don't limit ourselves or limit the approach to one client at a time. And then, most importantly, what's the cost of security in our approach? So an active attacker could forge authentication tokens, or they could simply be lost. meaning you send a request and no one answers. You send again a request and no one answers. So you increase, on the client side, you increase the counter, or decrease the counter of your hash chain again and again and again. So there's a disparity of the counter at the provider and the client. And that means the provider needs to iteratively try to recover the correct index, I, to decrypt the request he receives. That's the scenario of the active attacker, but that's also the expected scenario since you don't know whether there's any Wi-Fi access point that you'd like to share network in the vicinity. And what you can see is for a hash chain length of 1,000, even if you lose 999 of those hash tokens, the client lookup doesn't suffer from that, as does the reply to the access point. That's independent of the length. But of course, AES decryption you need to do 1,000 times. Hashtags you need to do 1,000 times as well. And there's an increase if you lose tokens in between. But even in the worst case of 1,000, that's still in the range of 20 milliseconds. So that's not too much work for a normal provider instance. We can live with that. And the provider doesn't need to deplete the hash chain, but could simply store the last successful recovery and do it again and again. As I said, this is the expected scenario as well. So as a conclusion, Wi-Fi sharing is great. We could leverage the potential of ubiquitous private networks. There's security and liability risks that we want to solve in this approach. We propose counts, where you have 802.1x equivalent authentication by leveraging the home provider trust relation. It's compatible to real-life mobile devices and access points, and there's very limited overhead. What I didn't mention before is you can have secure and intuitive accounting, meaning the access point could count what amount of traffic you forwards, and the provider could sign off on that. So you could have incentive schemes or micropayments based on that accounting, leading to happy accounts. With regard to the aforementioned Wi-Fi networks are bad because they ask you for passwords. We don't. This is all done automatically. Thanks for your attention.
Thanks for your talk. That's a very, very good idea. I got one question and one comment. So, my comment comes from the question, I think. You essentially seems to be very bound to actual internet provider at the moment. Is there any reason why? And can you see, essentially, could anyone deploy one home provider and be authenticated against that?
Yes, definitely technically. But, well, there was a lot of discussion when we did this for that. The point is, you could do that, but that would open up the possibility of providing rogue home providers that are not accountable. So the access point would not trust them and could not hold them accountable. So there could be a DNS or something, and they could be gone the next day. So there would be accounting, and you would get traffic forwarding, so we opted against that possibility. We stayed on the safe side, if you want. But technically, it's no problem at all. You could derive the provider ID against an IP address from DNS. That's no problem at all. But for the time being, we opted against that.
All right. So my understanding from your talk is that you actually established an OpenVPN connection to the home provider. So essentially, your hosting AP is not forwarding any of the traffic itself, and it's eventually the home provider who forwards all the traffic.
To the internet.
Yeah, so they would still be accountable. Like they would be the exit point for your forwarding.
Yes, it goes more into the direction of why would you cooperate in terms of Wi-Fi sharing. So that's not an altruistic thing, or typically the altruistic thing doesn't work. If you would have micropayments or incentive schemes, which we discuss a bit more in detail in the paper, and you would have a home provider that is gone the next day, there could be no accounting. Maybe I didn't say that clear enough, but time's up.
Just my comment was that's also very similar to the sort of things that mobile IP would be lacking in terms of authentication to the access point, because after that you could actually reuse the same mechanisms that mobile IP already has, rather than opening an OpenVPN session, just use all the forwarding and home agent rules and these sort of things.
Good point.
So that would be interesting to see, but thanks.
Let's discuss. I haven't thought of that, to be honest. Good point.
Thanks.
you're using these probe requests, and when you broadcast them, there may be a number of access points, and if you receive multiple response, what happens?
That shouldn't happen. You broadcast it to all the access points in the vicinity, and if all of them decide to authenticate the request to the home provider, one of them will read first. And all the other requests that come after that will have a authentication token that's not fresh anymore, so they will simply be dropped. So the home provider will only always answer to one of those requests, one access point. So there should only be one access point at a time.
And the other question is, this is similar to AWS authentication framework. So you need to change the firmware on that access point, and how much work is that cost?
So if you use an access point that, for example, runs over WRT as a source access point software, it's only a change in software, and it's 200 lines of code. It's easily done, and we made the software we used for this on-demand network instantiation and the overhearing of the probe request. We made that public. That's the computer. So I wouldn't say it's a lot of work, but of course you're right. There's a step in deployment. It's an opt-in approach, so you could deploy that software on your access point and participate in the scheme. That's the nature of this collaborative cooperation.
Consider that an incentive, like we can give incentive, and people will deploy on WRT.
Okay, just take one last. We're sort of running over here.
Yeah. So hi, my name is Chetan. I'm from University of Missouri, Kansas City. It looks pretty similar to the authentication which HLR and VLR does, like home location register and visiting location register, right?
Yes.
So instead of forwarding your request to HLR, why don't we involve VLR right there, if it's possible? It will save us a lot of time.
I don't have an answer from the top of my head. It's a basic scheme we propose. We could adapt it to multiple use cases. I would like to discuss if you have any thoughts on that.
Okay, sure.
All right, I'm sorry. No definite answer.
All right, thanks.
Let's thank Hanno. Before we all head out for lunch, Ken has a very short announcement about dinner.
5 words. The schedule is wrong. Dinner is not at 6 o'clock. Dinner is at 7 o'clock. Dinner at 7 o'clock. Either here or on the beach. 7 o'clock dinner.